Hello, I'm Spiros Miselis. I will be presenting full rates of exercise throughout the year for IB exams, and I hope it helps your case. Hello again. We continue with Chapter 1, the unit of the gas laws. Let's know gas condition characteristics. Even a container containing gas A, if we want to describe the gas state, we must state the number of mole, the pressure, the volume, and the temperature. Gas characteristics are interconnected by the ideal gas equation. Pressure times volume is equal number of mole times gas constant times temperature. We know that the number of mole is equal with the mass of gas divided by molar mass. And we have the equation. This equation allows us to determine the MR of a gaseous chemical compound. Now, even the conversion of in condition 1 to the condition 2 with the number of mole constant. We have a gas A, number of mole N, pressure, volume, and temperature. And we convert the condition 1 to the condition 2. We have a gas A, the same number of moles, a new pressure, a new volume, and a new temperature. This conversion we apply with the equation which is known as the combined gas law. So we have the cases. From the combined gas law. First case. In the conversion, we have the number of mole, and temperature constant. So we have the new equation, which Boyle's law. Second case, we have the number of mole and the pressure constant, and the new equation is with the equation of Charles' law. In the second case, we have the number of mole and volume constant, and we have the new equation, which is known as Gay-Lussac law. Let's see some examples. In the ideal gas equation. First example. Calculate the molar volume of a gas at 27 degrees Celsius and pressure 200 kilopascal. Let's see the solution. We write first the ideal gas equation, which corrected the gas characteristic. The gas constant R is given, but we have to be careful for the units of pressure, volume, and temperature. So we have pressure is equal to 100 kilopascal, and we have to convert it to Pascal. So we have 200 times 10 to the cube Pascal. Volume, we have to find it in meter to the cube. The number of mole is 1 mole because we have to find the molar volume. The constant is given. And the temperature we must find in Kelvin degrees. So we have 273 plus 27 to convert Celsius degrees in Kelvin. So we can find the number of molar volume. Be careful with the units. So we have so the volume is equal and the volume is 0.0125 meter to the cube. If we convert to dm to the cube, we find so we have the answer. Mass volume is equal with 12.5 dm to the cube. This is an example for the ideal gas equation. Let's see example 2. Calculate the mass of methane occupying volume 200 dm to the cube at 27 Celsius degrees and 100 kilopascal. We have one condition for the gas and we'll use the ideal gas equation. So we have and we know pressure is equal 100 kilopascal and we have to convert to Pascal. So we have 100 times 10 to the cube Pascal. Volume 200 dm to the cube. We have to convert in meter into the cube. So we have 200 times 10 minus 3 meter to the cube. Then we have the number of mole is equal with mass divided with molar mass. So we need the molar mass. For methane, MR is equal with 16.5. So we have mass and molar mass. The gas constant are given. And the temperature we find degrees Kelvin. So we have 273 plus 27, so we have 300 degrees Kelvin. So we have and we find from the equation the mass, which is equal and we find mass is 128.76 grams. Let's see example 3. An unknown organic compound has empirical formula carbon hydrogen 2 5.61 grams of the organic compound occupied volume 30 centimeter to the cube at 27 degrees Celsius and 83.1 bar. Specify the molecular formula of the organic compound. Let's see the solution. We have again one condition for the gas, so we'll use the ideal gas equation. So we have the ideal gas equation and then pressure is equal with 83.1 bar, and we have to convert to Pascal. So we have 83.1 times 10 to the 5 Pascal. Volume is 30 centimeter to the cube, and we have to convert to meter to the cube. So we have 30 times 10 minus 6 meter to the cube. Now we have the number of moles, which is equal with the mass of compound divided with the molar mass. We don't know the molar mass. We're asking for molar mass. So we have 612 grams and the unknown MR. We know the constant for the gas, and we find the temperature in Kelvin degrees. So we find the molar mass. So we have and the molar mass is equal and we find molar mass is equal with 56.12. So we can find the empirical form, the MR from empirical formula. Is 14.03. So we have the mass from empirical formula times N is the molar mass we find from the ideal gas equation. So we find the number of N, which is equal with 4. So the molecular formula is carbon 4, hydrogen 8. This is a method of determine MR. Let's see example 4. A gas has density of 1.75 grams Dmet minus 3 at 47 Celsius degrees and pressure 90 kilopascal. Determine its molar mass. Let's see the solution. We have a condition for the gas, so we use the ideal gas equation. And we have pressure is equal 90 kilopascal, so we have to convert to Pascal. Density is 1.25 means that if we have mass 1.25 grams, this mass occupied volume of 1 Dmet to the cube. So we can say that if we have volume 1 Dmet to the cube, you have to convert to meter to the cube. So we have the meter to the cube, and from the mass we find the number of mole. So we have 125 grams divided with molar mass. Also we have the constant gas, which is given, of course, and the temperature in Kelvin degrees. So we have and from the equation we'll find the molar mass of the gas, which is equal with 36.93. So we have the answer for the problem. This is also a method to determine MR. Let's see example 5. For the experimental determination of molar mass of nitrous oxide, it was determined that 37.86 grams nitrogen oxide occupies a volume of 40 dm to the cube at pressure 80 kilopascal and 27 degrees Celsius. Determine the percentage error of the method. Let's see the solution. We have one condition for the gas, so we have to use for the experimental determination the ideal gas equation, and we have pressure 80 kilopascal, so we have to find Pascal. Volume 40 dm to the cube, so we have to find meter to the cube. The number of mole is equal with the mass divided for the asking molar mass. So we find from the experimental results the experimental molar mass. So we have that molar mass is equal and the molar mass is 29.50. So we have the theoretical determination using the molecular formula of nitrous oxide. So we have MR is equal with 30.01. So we can find the percentage errors. The percentage error is equal from the molar mass we find theoretical minus the molar mass we find experimental, and we divide it with theoretical molar mass times 100. So we have 1.70 percentage error. Let's see examples to the combined gas law. First example. The molar volume of a gas is 22.7 dimeter cube mole to -1 at STP, with the molar mass at 27 degrees Celsius at the same pressure. We have two conditions for the gas with same mass, so we write the combined gas law. So we have and we have the same pressure, so we have the formula, and we substitute into the equation. So we have and we find and the molar mass is equal 24.95 dm to the cube. So the answer is that molar volume is equal 24.95 dm to the cube mole to -1. Be careful. in combined gas law, pressure, volume, and temperature must have the same units. Let's see example 2. Amount of methane occupies volume 40.50 centimeter to the cube at pressure 80 kilopascal and temperature 27 Celsius degrees. What is the volume of the amount of methane at pressure 120 kilopascal and temperature 47 Celsius degrees? Let's see the solution. We have again two conditions for the gas with same mass. So we use the ideal, the combined gas law. So we have and we know for the first condition the values of pressure, volume, and temperature. And for the second condition, be careful to have the same units for pressure, temperature, and volume. So we have substitute to the combined gas law, and we have and we find the volume for the second condition. And the value is 28.80 centimeter to the cube. Let's see Exam 3. Amount of carbon dioxide occupies volume 22.25 dm to the cube. At pressure 100 kilopascal. The same amount occupies volume 125 dm to the cube at new pressure. If the temperature remains constant, calculate the value of new pressure. Let's see the solution. We have two conditions for the same amount of the gas, so we use the combined gas law. So we have the combined gas law, and we have also the same temperature, so we have the equation. And for the first condition, we have the pressure and the volume. For the second condition, we have the asking pressure and volume. Be careful to have the same units. So we have the asking pressure is equal and the value is 65.80 dm to the cube. This is the last exercise to the gas law, and thank you for watching, and we have a new lesson soon. Thanks for listening, and more IB chemistry videos to come. If you like the video, and you can support me on Patreon. Thank you.